Welcome, everybody. Thank you so much for taking the time out of your schedules to join us today. I really hope the weather wherever you are is as glorious as it is this afternoon in Bristol. My name is John McWilliams, Director of Civic and Alumni Engagement, and I'm absolutely delighted to be hosting this online lecture for our wonderful University of Bristol alumni community. I'm joined today by Dr. Hannah Wakeford, who's going to be telling us about the weird and truly wonderful world of exoplanets, which are planets which orbit stars other than the Sun. Before we get into that, just a few housekeeping items to make you aware of. There's going to be some time for Q&A at the end of the presentation. You'll see a Q&A panel, or you should see at the bottom of your screens, and you can submit questions here at any point as they occur to you. We've already had really quite a number of very interesting questions come through before the event, and we're going to try and answer as many of these as time allows alongside the live questions. So with that preamble and without further ado, I'd like to open today's event. So welcome to Dr. Hannah Wakefield. We're really delighted to have you here with us to talk to our alumni community. Hannah is Associate Professor of Astrophysics, and she leads a research group that uses space telescopes to examine alien worlds. She's a recipient of the Fowler Award from the Royal Astronomical Society for her trailblazing work in advancing our understanding of exoplanets, and is a former NASA research fellow. So with that, I'm going to hand over to you, Hannah, to talk to us. Thank you very much.
Great, thank you. So, as John said, I'm going to be talking to you about exoplanets and taking you through some of the things that we do here at the University of Bristol and some of the discoveries that we've made in the team that I lead here. But I wanted to start by actually introducing you to our astrophysics group here at the University of Bristol. We have a really nice big group of people who are dedicating their time to understanding the nature of our universe, from ginormous galaxy clusters and an understanding of the entire universe and the way in which it operates, down to the black holes at the centers of galaxies, and to those planets and nuances that occur on those planets. How did they form? What are their environments like? So we cover a huge range of things and a huge range of really amazing people that do that. We actually work across a whole range of instrumentation, from the supercomputers that we run here at the University of Bristol. Bristol is the hub for Isambard AI, the next generation of supercomputers, and all the way up to telescopes a million miles away from the Earth, which I will be talking to you about today. And for our students, we actually operate a radio telescope on the roof of physics. If you've ever been to Bristol, if you look up towards the tallest hill, there's a big dish pointing towards the sky. That's us at the physics building. And we have these smaller telescopes, which we use for our undergrads. But we're actually looking to upgrade that radio telescope. It's incredibly old now. So we're hoping to get a newer version of the telescope with better access for students and better science projects for our students. So hopefully that's something that we can do in the future. But what I'm going to talk to you today is exoplanets. So what is an exoplanet? You already heard from John that these are planets that orbit stars outside of our solar system. So they're not actually part of our own system of planets which orbit around the sun. They orbit around the other stars in the sky. And this thought of planets existing beyond our own solar system is not new. The thought goes back to some writings that were done in ancient Greece in 450 BC by Epicurus, which stated that there is infinite number of worlds, both like and unlike our own. But it took until the 1600s, in the age of scientific enlightenment, to actually start postulating ways in which we can look for those planets and start trying to understand what's going on. And now, when we look up at the sky, we know that nearly all of the stars in the night sky will have planets of their own orbiting around them. And what I'm showing you here is a map of our night sky. So you can see in this nice wiggle across the middle here, this is our Milky Way. So this is the whole sky. You can only see half of the hemisphere of the sky from where you are. And this is a map of our whole sky, and every single one of these dots is showing you a star that has a known planet orbiting it. So these are the confirmed exoplanet host stars, and the color of those dots represents the temperature of the star. So the redder the dot, the colder the star, the bluer the dot, the hotter the star. And the sun, so the star that we are orbiting, would be a kind of light orange color in here. And I've highlighted in particular one region of the sky and zoomed in on that. And the reason for that is that this is a part of the sky where we pointed a single telescope for over 3 years. It was called the Kepler Space Telescope. And why I really love this is because what you can see in that zoom in is actually the detector, the CCD footprint, the camera footprint on the sky. So there are gaps in our knowledge of which of the stars host planets. And that's literally because there was a gap between our cameras. Because of the way in which you construct the telescope, there's always a little bit of a gap between your detectors. And you can see the architecture of the engineering imprinted on the knowledge that we obtain across the sky. And I always find that really exciting to see. But one of the really important things to realize is that when we're looking at these exoplanets, they're actually really close to us in the Milky Way. So now I'm showing you a map of the Milky Way, and right down here on the Orion spur of the Perseus arm of the Milky Way, this is where we live. This is the sun. And what I'm going to do is I'm going to play this forward, and you're going to start seeing dots appear. And each of those dots that appears represents a star that has a planet around them. And what I want you to notice as we go through this is the location of all of those dots. So we're starting to see those dots appear, the location of all of those stars with those planets. And you'll notice that they're incredibly close to the sun. And what that's telling you is that all of those stars in the sky that we're looking at, they're in every single direction, but they're all incredibly close to us, relatively speaking, in terms of our galaxy. So while we know that there's nearly 6,000 of them, if you extrapolate that across our galaxy, there are millions, billions, trillions of planets. And I like to say that there are more planets than stars, and we know that there are more stars than grains of sand on the Earth. So just think about the vast numbers of planets that exist out there. Now, there's a couple of spikes that you can see on here. One particularly noticeable one is that green spike towards the center of the galaxy. That's using a method called microlensing, and that's actually looking at these distant bright stars to see invisible planets pass in front of them. So you have to look at a really dense part of the galaxy so you can get as many bright stars to look at as possible so you can see those invisible signatures. But if you see in our zoom in here, this spike out the side here, that's our Kepler field. And the reason why it's this narrow spike is because we were looking at a single point on the sky for a really long time, so we can look further away. So this ends up with two different kinds of surveys that we get. These are called narrow deep surveys. So we're looking over a small area, but we're looking far away. Or shallow wide surveys, we're looking over a really wide area, but very nearby. So those are the two kind of things that have allowed us to discover these thousands and thousands of planets in the sky. And when we take the information that we've gained from all of these planets, what I'm showing you here is the size of the planet, so the radius of that planet, versus the number of planets that have been discovered with that radius. And that's actually in a relative value there. So that's not an absolute number on the side there. That's a relative value for number of stars as we extrapolate it out. And I've put little lines on here to show you relative to our solar system, the sizes of the planets that are being discovered. And one of the first things that you can notice from this is that a majority of the planets that have been discovered have a size somewhere between the Earth, our largest rocky planet in the solar system, and Neptune, our smallest gas giant in the solar system. So in fact, a majority of the planets that have been discovered so far are not represented in our own solar system. And that is really in itself an exciting discovery that our solar system doesn't have the typical planet in it. But I know it's really hard to kind of put this in perspective. So I'm going to invite you to kind of imagine with me a fruit basket of planets. Now, in this wonderful fruit basket, we're going to start with the Earth, and that's going to be the size of a pea. I understand that's not a fruit, but the Earth's always going to be that standout, unique world. So it should be the pea in our fruit basket. As we go through the other sides of the planets, you can imagine that Neptune and Uranus, these small ice giants really far out in our solar system, they're about the size of a plum. And our Saturns and our Jupiters are about the size of an orange. If you look at these two different parts of this histogram, so these two different peaks that you can see between Earth and Neptune, we actually have what are known as the super Earths. So these are larger than the Earth, so they are super Earths. They're about the size of blueberries. And then our mini Neptunes, so they're smaller than Neptune, mini Neptune, they're about the size of grapes. So when we're looking at this, we can see relative sizes of all of these planets and get an understanding of what they might be like. So the size of our planet can help us understand what does that world seem to be made of. But one of the really key things about the planets that we've discovered is that they're in a very different location than the ones in our solar system. So what I'm showing you now is the separation of that planet relative to its star. So you can see along the bottom here, number one is the Earth. So we use the astronomical unit, the distance from the Earth to the sun, and you can see the Earth sitting right here. So now we're measuring the size of the planet, the mass of the planet versus the distance from their star. And you can see our solar system planets all up here. But all of our exoplanets, our fruit basket of exoplanets, all exist much, much closer to their stars than our solar system planets do to the sun. And a lot of this is to do with observational bias. It's much easier for us to detect planets that are much closer to their stars because they affect their stars more greatly than when they're further away from it. So we can see the effect these planets have on their stars because they're much closer in. But also, because they're much closer in, their orbital periods, their year, is actually shorter than our year. So the closer you get to your star, your year gets shorter and shorter. And because your year gets shorter and shorter, it allows us to actually measure the orbit of these planets multiple times before we can be certain that we are measuring a planet around that star. So because they're close in, it allows us to get that confirmation of the detection of these planets as well. But one of the strange things is that a lot of these planets are orbiting incredibly close to their stars. And we hadn't even considered that before when we had the data point of one, which is our solar system. So we were learning new things about the demographics of these planets as well. What are they like? In general, when we look out into the galaxy, we're not seeing something immediately similar to our solar system. And one of the really cool things about these planets orbiting really close to their star is that they're going to be what is known as tidally locked. So this means that the rotation period of the planet itself, so the way it rotates about its axis, is equal to the time it takes for it to orbit around its star. And this ends up looking something like this. So the planet's actually rotating, but it's also orbiting at the same time. And you end up with a permanent day side facing the star and a permanent night side facing out into space. And we can actually see this effect really clearly in our solar system. If you look up at the moon, you'll only see one face of the moon from the Earth. You will only ever see one side of the moon. And that's because the moon is actually tidally locked to the Earth. It rotates about its axis every 28 days, and it orbits around the Earth every 28 days. So you end up with the fact that we only ever see one face of the moon that is pointing towards the Earth, and one face is always pointing out towards space. So now you just replace the Earth with a star and the moon with a Jupiter-sized planet, and you end up with these really typical exoplanet systems that we're studying here at Bristol. But one of the really interesting things is that not all star systems are like our own. They orbit different kinds of stars as well. I already showed you the array of different colored dots that you get when you plot up how bright the star is, how hot the star is. And what you're seeing here is the effect of those different types of stars. So we orbit this medium, warm, yellowish white kind of star. And the peak of our star's light comes out in the optical. So that's the light that we can see with our eyes. But if you go to a small, cool red star, known as a red dwarf, a lot of the light actually comes out in the red portion of the spectrum. And then if you go up to these big hot blue stars, the light comes out in the blue part of the spectrum. So the type of light that is shining on these different planets is going to be different than the kind of light that we experience here on Earth. And that's going to change the way in which different things on the planet are going to react to that radiation environment. And one of the key things that we can take from that, because it's directly related to the temperature of the star itself, is we can actually look at how that's going to affect what is known as the habitable zone of our stars. So I've called it here the possible surface liquid water zone. Okay, so the habitable zone is this wonderful, fanciful region in which a planet could be habitable. But actually, the definition is a statement that says that liquid water could pool on a surface if a surface existed. Okay, so we've got this kind of distance from a star that we can measure where you can get liquid water. So we need to be between our 100 degrees at the closest approach to the star and 0 degrees at our furthest approach from the star. And we need to have a surface in which that water that can exist at those temperatures can actually pool on the surface for it to be this habitable zone planet. And when you take that habitable zone, that possible surface liquid water zone, and you plot it again, we've got distance from the star along the bottom here. But now we're looking at the temperature of the stars with the sun up here in our solar masses of one. You can see our solar system planets, the Earth right in the middle of that wonderful possible liquid water zone. But as you go down to these cooler and cooler stars, which are the most populous stars in the entire galaxy, there are more of these M stars than there are of these solar type stars. You have to be much, much closer to those stars to be in this liquid water temperate zone. So often the planets that are orbiting these small red stars in this temperate region will actually be tidally locked to their stars. So you end up with this very alien environment in which they're existing. One of the things that I work on is really studying and understanding the role of atmospheres in planets and their climate. And a planet's atmosphere plays the biggest role in the temperature of that planet and changing the temperature of that planet. And I'm just showing you a cartoon here of the way in which that solar radiation comes into our planet. It can bounce off our atmosphere. It can bounce off the surface of our planet if we have a surface at all. It can bounce off clouds, but it's actually also absorbed by our planet. So we get this absorbed light, and then that's re-radiated in the red, in the infrared as heat. So you can feel that in the morning when you touch the ground, it's cool because it's been cooling overnight. And then at the end of the day, especially a beautiful sunny day like today, if you touch the ground, it'll be very, very hot. That's not just the radiation that's coming in, but it will be emitting that radiation as well. It's absorbed it and is re-emitting it. So that's escaping through our atmosphere and going out into space. But it can also be absorbed by our atmosphere and further heat up our planet, or it can bounce off clouds and be reflected back down, and you can end up with this cycling process of your radiation. So the atmosphere that you make around your planet really controls what the environment is actually like on the world that you're looking at. And we can actually see this in the Earth's atmosphere. These are two satellite images of the Earth. And I'm showing you on the left the reflected solar radiation. So this is the light that is bouncing off the atmosphere. So sunlight's coming in and it's bouncing directly off the atmosphere. And it's showing you from blue, where it is kind of the least reflective, to green and white, where it's the most reflective, like a mirror. And then on the right-hand side, you're seeing the emitted radiation. This is the radiation that's coming from our planet and going out into space. And one of the really cool things from this figure is that you can actually see the clouds themselves forming over the Amazon rainforest. So over here, we've got South America. This is the location of the Amazon. And we've got these big cloud structures here, which are both highly reflective, so they bounce the solar radiation away, but they also trap a lot of that heat that is being emitted from the Earth and not allowing it to escape into space. So the clouds play a massive role in the energy that a whole planet has in controlling where it comes in and where it goes out into space. So I'm really interested in clouds and how they change what's happening in these planetary atmospheres. But one of the other key things that we very rarely think about when we're taking snapshots of the universe, we get a single picture of what's going on. But we know that planets change with time. And that's no more true than anywhere but the Earth. I mean, this is a map showing you how Earth has completely changed its atmosphere and its climate over its lifetime. So if we go all the way back, this is our modern Earth at the bottom here. If we go all the way back in time, we had an atmosphere that was dominated by carbon dioxide and methane, a very carbon-rich atmosphere. And this is known as the Archean Earth. And the atmosphere would look a very hazy orange color at this point. We then see a really big change in the amount of oxygen through the Great Oxygenation Event, the emergence of cyanobacteria, which turn the carbon dioxide into oxygen. And then we start seeing, as we get to the modern era of the Earth, the emergence of the ozone layer, which can only occur when you have enough oxygen in your atmosphere reaching to high altitudes where it can interact with the sunlight and be generated and destroyed in a cyclical process. So we see the modern atmosphere is really only defined in the last 500 million years. So the modern Earth in which we inhabit is incredibly new. So when we're looking at these snapshots of these planets, we have to look at hundreds of planets in order to see those timestamps where we would expect things to be happening. And one of the things that I love about the Earth is that even though we're in this nice modern Earth, the circulation structure and the way in which radiation interacts with our planet and its atmosphere means that there are actually some rather uninhabitable places on our planet. And this is actually a picture that I took when I was in Death Valley in the United States. This is an amazing part of geology, and it has some of the lowest parts on the Earth. So you're actually below sea level for a majority of the time. It's insanely hot, and everywhere there are these signs that say stop extreme heat danger. Walking after 10 a.m. is not recommended. And what I absolutely love about this sign is it doesn't ever say when you can come back. It is not a place in which you want to be spending a vast amount of time. So, how do we take all of these principles? We understand that these planets are tidally locked to their stars, and that means that they've got this permanent day side and the permanent night side. We're looking at these planets and the influence that they have on their stars, but we actually ultimately, we have to know about their atmospheres. Otherwise, we can't understand what that world is actually like. So how do we go about measuring that? The method that we use to do this is known as the transit method. And what we're doing is we're looking at the stars themselves and we're not seeing the planet. So we're only looking at the star's light. And what you will see is in these graphs down here, this is what we would measure as scientists. We're looking at the star's light and we'll be measuring the amount of light as a function of time. So we'll look at it for a long time and we'll measure how much light there is. So if we play this, what you're going to see is we've got two planets passing in front of this star. Our star is the same, but the planet that we're passing in front of that star is a different size. So one of our planets is rather large and one is rather small. And what you'll notice is that for our large planet, it causes a larger change in the amount of light that we're seeing compared to the small planet. So this means that it's much easier for us to detect big planets in front of stars than small planets. And that's just simply because the sizes is a relative area blocked out by the planet relative to the area of the star itself. So the bigger the planet, the bigger the change in the light that we're seeing. So the easier it is for us to make that measurement. So a lot of the work that we've been doing in terms of understanding these planets has been focused on these large planets where we can get this really good signal from what we're measuring. So I'm going to talk about some of the results that we've been getting from these giant planets, but I'll show it in the context of how we're learning that across the board. Just to show you how we get the atmospheres of these, as that planet passes in front of the star, some of that starlight's actually shining through the planet's atmosphere before it reaches our telescopes. And what I'm illustrating here, this is a real color image of the Earth and the moon. And what I'm going to show you is what happens to that picture when I change what color of light I'm using to look at it. So I'm actually going to change the wavelength of light that I'm using to take this picture. And we're going to see how the atmosphere is transmitting that light. So how that light is being filtered through the atmosphere. So in this picture here, what we're now seeing is 8.6 microns. This is actually in the infrared. So this is heat we're measuring from this. So this is infrared light that you will be more familiar with as the nice radiation heat that we're getting from the sun. And then if we look at it in 9.6 microns, which is actually measuring the absorption of ozone, so O3 in our atmosphere, if I flick between these two wavelengths, what you'll see is the physical size of our planet appears to change. So physically, if I looked in this wavelength compared to this wavelength, I would think this planet was smaller than this planet. And that's because what I'm measuring is actually the absorption of material in the atmosphere, which is making the planet appear to be bigger. So how do we do that when we're looking at it in these transit events, so this time series? So now we're looking at different colors and we're building up that measurement of the depth of that transit. So we've seen all of those colors flash in, we've measured them as a function of time. And now we're going to plot up that depth, that arrow that I'm showing you there, as a function of the color, the wavelength that we're looking at. So this is now measuring the amount of light that is blocked by our planet as a function of our wavelength. And what we're seeing is that as we go to the red part of the wavelength, there's a spike in that. We're blocking more light than we were in the blue end of the spectrum. So if you think about traditional spectroscopy, if you absorb something, you block more light, so you end up with kind of a dip in the amount of light that you're getting. And that's exactly what's happening here. We end up with a dip in the amount of light we're getting from our star. But because what we're actually measuring is the relative difference, we actually flip that. So all of your absorption spectra are actually flipped over. So it's now a peak because our planet is appearing bigger because we're measuring the amount of light blocked. So I'm sorry to any of our chemists or engineers out there. We're taking all of that wonderful spectroscopy and we're just flipping it over to completely confuse you. But one of the beautiful things about nature is that every single atom and molecule absorbs and blocks light in a different way. It interacts with light in a very unique and fingerprinted way. And we can actually see how all of those fingerprints change the spectrum of light. So what I'm showing you here is if I change the amount of water in the atmosphere, in this case, I'm looking at a giant planet about the size of Jupiter, incredibly close to its star, about 1,500 degrees Celsius, so incredibly hot, hotter than in your oven. And what we're looking at here is water gas in the atmosphere and how it changes the amount of light that we see. So you can see it affects it across all of those wavelengths that I'm looking at. We can now look at carbon dioxide and carbon monoxide. And what you're seeing is the difference between those water bumps that I've kind of imprinted on there for you and the carbon species. They're much narrower bands, but they're also concentrated at the much redder end of the spectrum. So longer wavelengths, they absorb longer wavelength light. This is why they're such efficient greenhouse gases, because they interact with infrared radiation so efficiently. So when we're looking at these planets, we're looking for these fingerprints on the spectrum. And actually, if we've used the Hubble Space Telescope, and we have done for the last decade and a half doing this, and I started my career really working with Hubble Space Telescope data, what I'm showing you here is now a smattering of all of the measurements that we made with the Hubble Space Telescope across the planetary mass and radius space. So now we've got our solar system in here, so Earth down here, our gas giants starting here all the way up to our Jupiter-sized planets. This is kind of a proxy for the density of the worlds that we're seeing. And with the Hubble Space Telescope, we were able to measure a whole load of different sized planets, from these small rocky worlds down here up to these amazing gas giants with these very alien hot atmospheres. But one of the key things is that the Hubble Space Telescope has a wavelength limit, which means that we can only see up to these water bands in the atmosphere and some of these atomic species that you would get in the optical part of the spectrum. So to get that carbon species in the atmosphere, the CO, the CO2, and any other unknown absorbers in the spectrum, we needed to go to these longer wavelengths. So to do that, we had to design a brand new telescope, and that is known as JWST. So JWST was 20 years in the making, and it actually finally launched on Christmas Day 2021. And JWST is this amazing feat of engineering that started out with, I think it was 344 single points of failure on launch day. And today, after it has gone through this amazing transformation, it was folded up like an umbrella in the rocket so that it could launch. And over time, when it was in space, it unfolded, brought out its solar shield, and now it only has 10 lifetime single points of failure on it. So it was an amazing feat of engineering to get this launched and to actually have it be a functional telescope for us. And it's this beautiful 6.5 meter gold plated kind of honeycomb of mirrors. And the reason why they're gold plated is because they're very good at reflecting infrared light instead of the nice shiny silver mirrors that we have in our houses, which are fantastic at reflecting visible light. So we needed to have this gold plating that reflects this infrared heat of our universe. And it's doing all kinds of astrophysics. It's actually looking across the very, very first stars that formed in the early universe down to the most modern stars that are currently forming right now and the planets that are orbiting around the stars in our local galaxy. So, in the first couple of months of science operations, which began in June 2022, we had already seen these amazing images coming out of JWST. And this is hopefully something that you've been familiar with and you've seen across press releases and news articles, these gorgeous images of space, which are revealing new processes that are occurring that we hadn't been able to access before. But when it comes to exoplanets, we're not looking at pretty pictures. I've already told you we're looking at the stars themselves. We don't see the planets. So instead, we're actually getting data points with error bars. This is our spectra. These are the dots and the wiggles and the spikes that we want to be seeing so that we can tell you that this atmosphere has water vapor in it. This atmosphere contains carbon dioxide. And trying to understand what that means for the overall environment for those planets. So just to really highlight how JWST has changed the way in which we can measure exoplanet spectra, I want to show you this. This is a spectrum of a giant planet. It is about the same mass as Saturn, but it is the radius of Jupiter. So it's this really puffy, low density planet. It's orbiting incredibly close to its star, so its year actually lasts about 3.5 days. So it's tidally locked to its star with a permanent day side and a permanent night side. And what we're measuring here is the light that's being filtered through the atmosphere of that planet before it reaches our telescope. And the blue data that you're seeing on here, compared to our black model of what we expect we're seeing, these blue data points come from Hubble Space Telescope measurements and Spitzer Space Telescope measurements. And this is work that I published back in 2018 whilst I was a NASA fellow. What we saw for this planet is that we've got strong sodium absorption, potassium, and water vapor. This is in the gas phase. It's not a liquid in the atmosphere. This is not a habitable planet. It doesn't even have a surface. This observation set here took about 8 individual measurements of this planet that we had to go back over the course of many years to get. What I'm going to show you now is what happens with JWST with a single observation of this planet, which occurred in June 2022. With one single observation with JWST, we were able to learn so much about this planet. One thing that I want to point out is that now in gray here is the model that I predicted based on the data that I'd obtained from the Hubble Space Telescope. And now in black is the model that we're fitting to the new data from JWST. One of the great things that helps me a lot, feel good about this, is that the model in gray matches pretty well with the model in black. we made a pretty decent prediction about what we would be measuring. But there's a couple of things that we didn't expect to see that we missed. And I'm going to show you those on the next slide in a kind of typical way that we look at them. So what I'm showing you now, all of those lines in the background, that's our data. But I want you to focus on the white model. So this white line is now showing you the best fit to the data. All of these other colored lines are now showing you what happens to that model when I take out a particular gas in the atmosphere. So here we've got our CO2 feature, and we can tell you it's a CO2 feature because if we take the white model and we remove carbon dioxide from it, what we would measure is this yellow line here. We're very clearly not measuring this yellow line here, and therefore we've been able to detect carbon dioxide in the atmosphere. One of the really interesting things we saw that we didn't necessarily expect is the difference between this pink line here and the white line. This pink line is showing you what would happen if you had a planet without SO2 in the atmosphere, sulfur dioxide. And sulfur dioxide is made through what are known as photochemical reactions. The sun, the light from the star itself comes in, interacts with the gas in the atmosphere and produces new chemistry. So this photochemistry had been theorized, but never proven. So these first observations, which were actually led by one of my PhD students here at the University of Bristol, showed the first evidence of photochemistry happening in a planet orbiting around another star, which was incredibly exciting for our chemists. But one of the most exciting things for me in this is the difference between this white line and this really dark line, which dips all the way down here. This really dark line here shows you what this atmosphere would look like if it didn't have clouds in its atmosphere. And I've already told you that clouds play a huge role in how the atmosphere of a planet is controlling its temperature and distributing its heat. And one of the key things for these planets is we can look at the temperature of the planet as a function of the altitude, and we can ask what kinds of clouds should be forming. And one of the things that's really cool is that you can look at the difference in the altitude where you place those clouds in the atmosphere will change the way in which you absorb the light and block that light. So if you change the position of the clouds, then you change how much light is coming into and out of your planet. If you change the sizes of the particles of your clouds, you change how scattering it is. So this is saying how much bigger in the blue end of the spectrum our planet looks compared to the red end. So we see scattering on Earth. If you look out, if you see clouds, they're white. Water is incredibly scattering. And the smaller particles you have, the more scattering that light is going to be. So if we now take this and we look across all different kinds of temperatures, I've already told you that some of these planets we're looking at are incredibly close to their star. So in the thousands of degrees, we start changing what the clouds are made of. We've got our temperature pressure profile. So we're going up in pressure, down in pressure here, up in altitude. And we've got the temperature of the Earth in green here. And you can see that we crossed the water line here. So this dashed line is telling you that when you reach saturation, 100% water in the atmosphere, it's going to form a cloud. So on the Earth, we have water clouds. We can all look out our windows and see that we've got water clouds in the Earth's atmosphere. In our solar system planets, we have clouds of methane in our coldest ice giants or ammonia in our Jupiters and our Saturns. We've got these very, very cold species which form these really solid ices. But at the high temperatures of the planets that I'm looking at, these giant planets incredibly close to their star at these insanely hot temperatures, the clouds that are making up their atmospheres are actually made of things like disodium sulfide, a sticky yellow substance that you dig out of the ground. Magnesium silicates, quite literally sand on our beaches, are made of magnesium silicates. The glass in our windows and on our laptop screens are all made out of magnesium silicates. The clouds are made of molten iron droplets. And my favorite, the corundums, the aluminium oxides, which on the Earth form the basis of rubies and sapphires. So the clouds in these planetary atmospheres are made of incredibly different substances. So my question is always, how does that change the way in which it affects the planet and its climate? we've been really looking for these kinds of clouds and trying to understand what they're like. And one of the really cool things about the universe is just like our atoms and molecules, these minerals have their own unique fingerprints. They absorb light in a very specific kind of way. So if we've got our small particles of our clouds, we have both the scattering component in the optical, so we're seeing scattering over here, and in the mid-infrared, right at the edge of where we're measuring these atmospheres, we're seeing this absorption feature, which tells us that we have a magnesium silicate cloud in this particular atmosphere. And when we're looking at different atmospheres, we have to think about what material is available to them. So what material is available on the formation of those planets in the disks around the stars as they're being formed. And you can look at the abundance, the amount of different materials across the universe, and you'll see that we'll be most likely to be making these silicate clouds. These silicate clouds are going to be magnesium silicates because we have lots of magnesium in silica. And you can actually see those in those big dust clouds that are forming those stars. Those motes of dust that you see are all magnesium silicates. So we fully expected when we were looking at these giant hot planets that the clouds themselves would be made of this sand. But what we actually measured when we looked at this with JWST, our team was making a measurement of this particular planet. We were really excited. We expected there to be clouds. We'd already measured with the Hubble Space Telescope scattering in the optical part of the spectrum. But when we measured it, we saw this spike in our data. Very different than what we expected from our magnesium silicate feature. So we had to go and question what is this absorption feature, which is clearly not what we expected it to be. And the exciting thing is we went back to a database that I created when I was a PhD student, and we looked through all of the different minerals and rocks that it could be that are forming in this atmosphere. And we took their spectra, which are using optical properties that have been measured in the lab, and we compared them to the data that we're getting from this planet. And what we actually found is that we have solid quartz clouds that exist in the atmosphere of this particular planet, which is known as WASP-17b. It sits about 3,000 light years away. It's a fairly close by planet in relative astronomical terms. And it is about the size of Jupiter, but it's half the mass. So it's an incredibly puffy planet. And what you're seeing here is similar to the spectrum I showed you before. In the white dots are our data. And what we're doing is we've got our purple model. And now if we take out these quartz clouds from the atmosphere, what we would get is our yellow model here. So what we're showing you is that we've got absorption from this SiO2 solid quartz crystals forming clouds in this planet's atmosphere relative to what we would expect from that planet if they didn't have quartz crystals in its atmosphere. And this was work that was done in a press release from the University of Bristol back in 2023 by one of my postdoctoral researchers. And it's a really exciting result that we are just taking forward and learning more and more about on other planets. This is the first time that the clouds, which had been theorized for years and years, over 2 decades of theory linking to the fact that these clouds must exist in these atmospheres, to the first detection that was led out here at Bristol. And when we combined that measurement that we made with JWST, so in red here, I've got my JWST data, with our Hubble Space Telescope data, we were actually able to use that scattering component that I showed you, which tells you the sizes of the particles that are scattering that light, with the absorption feature, which tells you the type, the material that is forming those clouds. We're actually able to now tell you that WASP-17 has these quartz crystal clouds, which are just a fraction the width of a human hair, but that they're traveling at thousands of miles per hour around this planet in about 2,000-degree heat. So all that to say that some of the most exciting planets out there are most certainly not habitable. This does not have a surface. It is a Jupiter-like planet, so it is gas giant. It's incredibly close to its star. It's got a permanent day side and a permanent night side. That causes thermally driven winds of the thousands of miles per hour I'm quoting here, temperatures in the thousands of degrees because it's so close to its star. It's about a 4.5 day year around its star. So in under a week, it's orbiting around its star. And because of these temperatures and because of the environment in which it's forming, the clouds themselves aren't made of water. They're made of crystalline quartz. And I've got a couple of examples here that you might have seen if you've ever gone hiking in the UK and you see seams of white crystals. That's quartz that you're looking at. The Earth is made up of about 60% magnesium silicate. And we can see these pure, beautiful quartz crystals all across the Welsh Mountains. So you can see actually these material here on Earth that are forming clouds in the atmosphere of these alien worlds. So I want to leave you with the thought that our solar system is full of unique atmospheres. The Earth is only one of those incredibly unique worlds. There's even a sneaky moon in here, which has a substantial atmosphere and has its own weathering cycles that we've been able to measure. So, with all of this diversity in our own solar system, we're now starting to explore the amazing diversity of the atmospheres of exoplanets and starting to understand the connection between the materials that make up the atmosphere and the nature of the environment that they make on that planet. So I'm sure that you have many questions, and I look forward to answering them. I want to thank my amazing team here at the University of Bristol. This is a picture of all of them who have contributed to the slides that I've shown you and the research that we're doing here. And we've got so many exciting discoveries that we're making for these incredibly alien, giant, and very hot planets, especially looking at and understanding how clouds will completely change the way an atmosphere reacts to its environment. So thank you.
Thank you so much, Hannah. This would be the moment where we all gave you a big round of applause. So let's imagine a round of applause in this very large lecture theatre of people we've got on. This event was hugely oversubscribed. It really was absolutely fascinating. So fascinating. We had 70 pre-submitted questions, as you know, Hannah, and the questions you probably haven't been following on the chat as you've been speaking, but have been rolling in as well live. And I'm now going to try and so thank you all for all those questions, by the way. It's so good to see such enthusiastic interest in this topic. But apologies in advance if I don't get to your specific question. I've been trying to wrap up and sort of put them into categories. Just the first one, this may be a quick one, I don't know. Daniel asked live, and it chimes with questions we'd had in the run-up as well. What kind of telescope would it take to get actual images of the planets, or is that just impossible? Daniel adds, and yeah, so that would be a really interesting one to know.
So it's actually not impossible to get an actual photograph of a exoplanet. And we've done it a number of times from both telescopes on the ground. So you can do it with a very large telescope on the ground, and the extremely large telescope, which is currently being built in Chile, is a European venture to build a 30-meter telescope, which will be an expert at taking direct pictures of exoplanets. We can actually use JWST to get direct pictures of exoplanets as well. And the way in which we do this is we use what is known as coronagraph. We actually block out physically the light from the star so that the light from the planets can shine brighter on our images. But the only kinds of planets that we can look at with that are very young planets. So these are planets that have only just formed. They also have to be really far away from their stars so that we can actually see the light separate from the star itself. The star's incredibly bright. So the ones I was talking about that are very close to their stars, we can't get an image of at all. They're kind of, the brightness of the star overtakes everything. But these very young, very distant planets are shining light out themselves into the universe, because when a planet first forms, there's a lot of energy in all of that material coming together, and it radiates that energy out into space in the form of heat. So if we look in the infrared, again, we can actually measure the light from these very young, very giant, long orbital period planets. So it's a completely different phase space, a completely different type of planet to the ones that I've been talking about today. But it is possible.
the opposite answer to what I was expecting, actually. So that's really exciting. Now, we have to get to the question of, we could put it a number of different ways, the alien question, or put it another way, how can we determine, lots of questions came in about this before and some during as well. Can these planets host life? Can we go there? How do we determine if they do or could host life in any way? I'm sure almost everyone listening to that is wondering that question in their mind. So I'd love to hear your thoughts on that.
So there's quite a few different ways in which we can do that. With the method that I was talking about today, what we're looking at is those very, very small stars, because I already showed you that the smaller the planet, the harder it is to measure that dip. But if you change the size of the star to a very small star, you can start seeing these small planets as well, because it's a relative size difference. So small star, small planet, we get the same amount of dip as a big star and a big planet, because it's about the size ratio. So what we're doing is we're looking at these very, very tiny stars, these M stars, for these small planets going around them. And we found hundreds of them. Now, the problem is exactly what I showed you with that possible surface water zone. The smaller the star, the closer your planet needs to be in before it is in the right temperature range for liquid water to exist. So these planets are likely tidally locked to their stars. So already, even though they're at the right temperature, they're probably a very, very different environment to what we're used to here on Earth. So there's a lot of questions around what we need to detect in their atmospheres to be able to tell you that it's habitable. And the general consensus is that we need to detect multiple different molecules at ratios compared to each other that could not occur in nature. And this is the really big question, because there's a lot of materials that we measure here on the Earth that we go, okay, that material is only made by biology. The only way it exists on the Earth is because we put it there or some biological organism put it there. But there's a lot of evidence in chemistry and there's a lot of evidence in our solar system that we can measure these materials in other environments where there's definitely not life. So we have a lot of work to do in the chemistry lab, for a start, of trying to understand the chemical pathways of making lots of different materials so that we can know that certain materials like oxygen or methane or anything else can only ever be produced by life. It's a definitive, this can only exist if it's produced by life. We don't have that information yet. We don't have a good enough database of chemical species that tell us this is, if we detect this, this is a really clear-cut thing. But we also need to be able to measure lots of different species and their kind of relationship with each other. Because if you look at the Earth's atmosphere, it's the relationship between the amount of oxygen, which allows us to make ozone. It's the relationship between the amount of carbon dioxide and methane in the atmosphere that is out of balance with what should be naturally occurring. So if we measure lots of different things, we can start to build up that picture. And as with any bit of science, extraordinary claims need extraordinary evidence. So this is going to take many, many years, but it's something that the field is actively working towards. In terms of going there, I really do want to emphasize there is no planet B. All of our planets are known as, WASP 17b, TRAPPIST 1b, but there is no other planet for us. We need to make sure that we're understanding our own planet, our own atmosphere, the way in which it changes our environment so that we can make this a planet that can host life for our own. So while we've got these amazing prospects out there that we're using to understand a lot of this chemistry that we can't replicate, it's so important that we also make sure that we understand that there's no get out of jail card here. This planet is the one that we need to understand and that we need to look after.
Thanks very much. That's very, very exciting for the future and a good sort of a good learning from that. That segues quite nicely into another set of questions we've had quite a lot of, which is, what does this research on far-flung planets mean a bit more generally for our own planet? Do you have any more reflections on that?
I mean, there's so many different reflections. I mean, in the general term, astrophysics studies themselves have given us information about how Wi-Fi works. They've given us information on how to make different technologies. The JWST engineering side, there's so many things from that that wouldn't have been commissioned or learned if we didn't require it to go look out at the distant universe. So there's a lot of practical applications that astrophysics and the exploration of our universe has really, really taught us. And I think that one of the hardest things to think about is that all of that happens way later than what we're doing. So everything we're doing now and the innovations that are being made, they're not going to have an effect for 50 years. And we don't genuinely know if they will have an effect. But there's a lot of precedent to show that astrophysics has kind of changed the way in which we can use technology and deal with technology. So I think that's on a big picture level. It's hard to say what the immediate impact's going to be, but there is going to be one. But on the kind of very specific level, I kind of mentioned it before. I'm really, really interested in clouds, and I'm really interested in the way in which their presence changes the environment of a planet. So when we look at the Earth's atmosphere, about 2/3 of the Earth at any one time is covered in cloud, which is a ridiculous number, but it's true. It seems silly, but it's completely true. And I always say that I love clouds because I'm British and we've always got clouds. She says on the clearest blue sky day that we've got. But when we fly an airplane and we make a contrail, so a cloud produced by an airplane, you see them as the two stripes in the sky. That changes the amount of energy that is coming into the planet by 1%. So you're adding a very small amount of cloud and you're changing the entire energy budget of a planetary atmosphere. So the way in which we look at these other planets and understand the different materials and how they generate clouds and how they interact with the light is actually helping us inform the way in which we can transform our own atmosphere. And I'm doing a lot of work with the absolutely world-leading chemistry group here at the University of Bristol. The aerosols research group here is unbelievable. There's so many amazing scientists, and we're actually I'm my first token astrophysicist, and we're actually using what we're learning from these exoplanets to design experiments in the lab so that we can learn more about these different materials and how they interact in an atmosphere.
Fantastic. Thanks very much, Hannah. I'm just looking through the other questions here. Just one question that just jumped out now, and given there was quite a lot of stuff about exciting kit, I feel like this is one worth asking. Thank you, Keith, for that question that's just come in. What exciting new kit tools do you expect to have in the next 10 years? I expect that's a question you might well be interested in answering.
So 10 years in an astrophysics lifetime is incredibly short, is the first thing
Right.
that I'll say. But in the next 10 years, we've got a number
Yeah.
of telescopes that are going online. So the Plato telescope, which is mostly being led out of the UK, that's going to be looking for more planets around more stars. So we're going to be searching for more and more planets that we can do this follow up on and understand more about their atmosphere. So that's going to be detecting the planets for us. We then are leading in the UK, we are leading the Ariel ESA mission. So this is a telescope which will launch in, I think, the 2030. And this is actually going to be doing a survey of hundreds of exoplanets to try and understand what their atmosphere is like. So we're going to be using that information to build up a population picture of what the planets are actually like. But taking that like the next step further in astrophysics, we're always kind of what's the next mission and how are we driving that down the line? I already mentioned the ELTs, the extremely large telescopes, which will be on the ground and doing lots of amazing exoplanet research there. But a lot of the things in the future that I've been looking at is something that won't launch until after 2040. It's called the Habitable Worlds Observatory. It is the next major flagship mission that will be coming out of NASA. And hopefully, if we can get the backing, the UK Space Agency and the European Space Agency as well. And we're working across the UK right now to define what that telescope is going to be like. And me and my colleagues have actually written science documents which say, this is the science that we want to do in the 2050s. This is what we need to be able to measure that. How are you going to build me a telescope that will do that for me? So a lot of the work for things that happen very far down the line starts right now.
Fantastic. Um, that sounds very exciting as well. I've just got a question in. well, as I'm speaking, interesting questions are coming in. I'm sorry, but Fred has just asked a question about AI, and maybe I could make it a slightly more general question. You've talked a bit about interdisciplinary research. How does this fit in with other fields of research, including AI? We couldn't get through any presentation without mentioning AI, so thank you, Fred, for bringing that up. Do you have any thoughts about what are the key areas of collaboration for you in the future and all these exciting areas you talked about?
Yeah, so I'll address the AI thing immediately. So I actually have a postdoc at the moment who did their PhD here at the University of Bristol. They worked on AI and machine learning in algorithms and methods when applying it to radio data, looking at galaxies. So I had the absolute privilege of being able to hire her, and she's now actually working on trying to use these machine learning methods that she developed during her PhD to help us clean our data. So the data that we get from JWST is actually just this big streak of light across a detector with lots of other garbage and dots and noise in there. And what she's been doing is she's been developing this machine learning algorithm with our AI capabilities and our GPU capabilities here at the University of Bristol to actually clean that data more so that we can, what we're planning to do is we're going to be applying this to all of our telescope data. And that's going to allow us to point JWST at more targets, more stars, where we previously couldn't get rid of this noise. And this noise was really interfering. This method that she's developed is actually, she's taking it to the Space Telescope Science Institute in Baltimore in the next couple of weeks. And she's going to be showing the instrument teams there how we can use AI to actually clean our data and be able to use our telescopes more universally across the sky. So that's the direct AI one. But in terms of cross collaboration, exoplanets themselves are incredibly interdisciplinary. We need biologists, we need mathematicians, we need chemists, we need physicists, we need engineers. But one of the things that is always kind of overlooked is the connection with the arts. And what I've shown you today included quite a lot of artist impressions of the planets that we're looking at. We can't get direct information on what these planets look like, but as scientists, we can give you an idea of what color they look like. We can tell you how far away they are from their star, what color their star is, and how that radiation might interact with it, where the clouds might be on the planet. So we work with artists a lot to get impressions of what these worlds look like. And a traditional impression will be a picture, a digital picture that we create with one of these artists. But recently, I've had the absolute privilege of working with some musicians, both at the University of Bristol and at different places, where we're trying to create an artist's impression of a planet through the emotive feeling of music. So creating music, which through its melody and through strange different noises that we're introducing, helps you feel like you're traveling around in the atmosphere of these planets. So I think there's always the opportunity to cross science with arts. And I think that exoplanets is one of the best things for that, because like I said, we require absolutely everything. And I didn't even mention the geologists that I needed to talk to understand what sand looks like in the spectrum.
So highly interdisciplinary and great mention of the arts there. And actually, that we're going to have to wrap up now. Apologies, we're very slightly overrunning, but there's just one question that segues so nicely that's just popped in from what you were just saying, Hannah, and that is, what are the 3 books you'd recommend? And it's a wonderful traditional way to finish any sort of university event to say, ask a bit of further reading. Christopher says, sci-fi novel, whatever. What should we go away and read about this, if we were interested?
There's this amazing book called Firmament by Simon Clarke. He's a good friend of mine, so completely biased, but it's about the Earth. It's about the Earth's atmosphere and the history of how we learned about the Earth's atmosphere and all of the principles that he talks about in that. It's a popular science book, so it's a good fun one to read. All of the principles are the things that I teach in my classes. All of the things about how does an atmosphere change and how does it react to radiation and what does the circulation structure of a planet mean for life on that planet. So I highly recommend Firmament from Simon Clarke.
Right.
In terms of science fiction novels, there's quite a lot of really cool ones out there. I actually do like the Andy Weir ones for the kind of Hail Mary and The Martian. Not so sure about Artemis, but those ones I found really fascinating because they think about people. And if you're interested in people and terraforming stuff, then Kim Stanley Robinson's the one to go down, but it's a bit doom and gloom. So I'm not putting that on the list. But what I really enjoyed in terms of science fiction and thinking about alien planets and stuff is some of the kind of books where we're looking out into space and asking how and why. I grew up a Stargate fan, so I'm a massive Stargate SG-1 person, and I love thinking about planets and the propagation of environments and how we're looking for similarities across the universe. And I would say that The Expanse is a really dramatic version of that in terms of how we can look at our population as a species and moving out to other planets. There's a lot of doom and gloom
Wonderful.
sci-fi out there. I don't, I'm not here for the doom and gloom, but that's what sci-fi's really gone to, this dystopian, really strange worlds. So that's what you're going to get if you go sci-fi.
But thanks for giving us some other thoughts to go away with, inspired by that. So we're gonna wrap it up there. Slightly overrun. Apologies everyone for slightly overrunning, but there was just so much interesting stuff to get through in that question session. Again, apologies if we didn't get to your question. We really were overwhelmed with them. But thank you for everyone for submitting them. And finally, thank you so much, Hannah, for joining us today and giving us that really, really interesting, inspiring talk and sharing your time and answering our questions and expertise. And thanks very much to everyone who joined us today as well. We really hope you've enjoyed the session. Hope you've found it interesting and feel as proud of as I do, as I'm a Bristol alum myself, as well as working for the university, of the really important work we're doing as a university in this area. Please do stay in touch with the university. There are many ways to engage with us, and we'll just put a link in the chat that tells you all the ways you can engage with us in all sorts of different capacities. We also have a really busy program of events coming up in 2025 you might be interested in, including our flagship in-person event, Bristol in Conversation, called Stories from the Stage, celebrating modern theatre, on Friday the 6th of June. So please keep your eyes peeled for more information on that. And we'd encourage you to update your contact details on our online form. And we'll send details of how to do that in the chat box so we can, if you're interested, so we can continue to send you direct details of events and opportunities like that. So please stay in touch. Thanks again, Hannah. Thanks again, everyone. And go and enjoy the rest of your evening. Thank you very much, everyone. Bye.